All right. Okay, here we go. So, in the ancient world, they believed the earth was the center of the universe, and then you had water, air, and fire, because the sun and other heavenly objects were thought to be made out of fire. They obviously belonged up in the sky. And it was believed that these things, the planets, were fixed on spheres which rotated. Okay, so that was kind of the prevailing view of the ancient world. And there were some problems with this. One of the problems is what is called the retrograde motion of the planets. So if you look at the planets, and I'm not sure how well this video is going to go, if you look at the planets against the background of stars, then, so for example, right here, I don't know if you can see it, right here is Mars. And so Mars is generally right above Crater and to the right of Virgo, okay? But night after night after night, if you look where Mars is, Mars seems to change location. And so now Mercury is coming by. So these objects wandered in the sky. They didn't have a fixed position. Like if you look at a constellation, this star right here, which is called Alpha 2, is always in the same place in the sky relative to, for example, Beta. That's another star in Libra. So those are fixed. But these things that they call Mercury, Venus, Jupiter, Mars, they all wandered. And so they were called wanderers, which in Greek, the word for wanderer is planet. So they were called planets because they weren't part of the fixed stars. They were wandering in front of the stars. But it was thought that these planets were also just rotating around the Earth, just on a different sphere at a different velocity, okay? But here's something wild that happens. So watch Mercury right here. Mercury actually backs up and then keeps going. Did you see that? This is where you nod or shake your head. You see that? Mercury went backwards for a while. If you believe that the world is the center of the universe and that things are mounted on spheres which are rotating in one direction, how do you explain Venus going backwards? Well, that's hard to. So retrograde motion of the planets was a problem, okay? Copernicus was the first one who was able to propose a coherent explanation for why that was. And so Copernicus observed the skies for his lifetime. He made all kinds of measurements, and he published what is now called the heliocentric theory of the solar system. Heliocentric meaning the sun. Helio means the sun, centric meaning centered. So a sun-centered view of the universe. And that sort of makes sense because if you think about Venus and Earth, well, that's a bad one. Let me find a better picture here. But here's the idea. If you imagine the Earth is the center, and you imagine this, the sun is the center, and the Earth is going around it, then for a while, like Mars, for example, when we are passing Mars, because we are on the inside of the curve, so think about running on a track. When you're on the inside lane, you might pass somebody. So from your perspective, it looks like they're going backwards. Even though they're going in the same direction you are, you're just on the inside lane, right? So you can explain the fact that the planets sometimes seem to move backwards by imagining that the Earth and all the planets are going around the sun, okay? And the Earth itself is spinning, which is why the sun seems to come up and come down. So that was Copernicus. He was the first model that was proposed of a heliocentric universe. People generally received it well, even though this was 1543. This is the late Middle Ages. And it didn't cause a whole lot of stir. And there's this dude named Brahe, and he's kind of interesting because he's wealthy. He owns an island, and he builds the first known observatory. His observatory is located on this dark island, and he builds this cool observatory that has a dome, that has a glass ceiling, and in the glass ceiling, he has etched a coordinate system. And so imagine this for fun. For 20 years, every single night, he tracks the location of 1,000 different stars and planets that he could see over the night sky every night for 20 years. Okay? So you guys are 18. From now until you are 38, every night, all night, you lay on a platform staring at the sky through a grid, and you note the location of 1,000 different objects, where they are relative to each other. That's what he does. Eventually, he gets in trouble with the king, who is also his uncle. He gets ejected from Denmark. He lands in Germany, where he's joined by a young genius named Kepler. And the good thing is he was able to bring all that data with him. So Kepler's another interesting guy. Kepler was a brilliant mathematician, and he wanted to study astronomy. And right now, that sentence looks totally normal to you guys, right? But if you lived in the 1600s, people would be like going, what the heck? That would be like somebody saying they were interested in law and wanted to be a neurosurgeon, right? What do those two have to do with each other? Astronomy was about predicting the future. And it wasn't even called astronomy, it was called astrology. What did math have to do with astronomy? That's craziness. But he loved those two things. The problem with Kepler was he was sick. He had smallpox as a child, and he had very poor vision, and he had crippled hands. So if you can't see, how the heck are you going to study the sky and the stars, right? That's a problem. So, fortunately for us, Kepler ends up joining Brahe. So Kepler's the mathematical genius. Brahe is the dude with all the data and the good eyes, apparently. And they meet up. So Brahe dies eventually, but Kepler inherits his data and continues to study it and pore through it. And Kepler notices some patterns. And these are very interesting. They're called Kepler's 3 laws. Okay? His work verified the heliocentric model of the universe or the solar system, and it was consistent with evidence. And so here's what Kepler came up with. They're called Kepler's 3 laws. The first of Kepler's laws was he noticed that all the planets move in elliptical orbits around the sun. So an ellipse is a shape, which it's one of the conic sections. A circle is the points that are all a common distance from the center, right? An ellipse, if you take 2 foci and you take the distance from the object to one foci plus the distance to the other foci, that sum is always a constant. So Kepler figured out that planets follow ellipses. Some of them are less eccentric, so they're more circular, like Earth's. And some of them are very eccentric, like some comets that he observed. Okay, we think he actually observed Halley's Comet. He just didn't call it that. But all of these things circle the Earth. That's the first thing he observed. All the planets circled the sun in elliptical orbits. The second thing he noticed was about how fast they moved. Hang on one second. I had to go move to turn my lights on. So here's what he noticed. Let's say you take the sun and you look at planet A, for example, Mars. When Mars is close to the sun, it's moving fast. And when Mars is far away from the sun, it's moving slow. He wasn't able to exactly measure the velocity, but what he did notice was that if you imagine how much area is swept out by Mars in 1 month, so in 1 month it goes from A to L, if you find this area, that area is the same for equal intervals of time. So when Mars is far away from the sun, this purple area is the same as that area. So since it's farther from the sun, it doesn't move as far. So he found that the planets and the comets and everything orbiting the sun swept out an equal amount of area in an equal amount of time. Hey, that was Kepler's second law. And here's where it gets impressive. He pores over his data and he is able to look for a relationship. You know how we're always trying to get straight lines in lab? He's trying to get a straight line. He finds that if he plots the square of the orbital period, so he figures out how long it takes, for example, Mars to go all the way around the sun back to where it started. That's called the orbital period. If he squares the orbital period and plots that on the x-axis, and he takes the average distance from the sun, that's called the semi-major axis on the ellipse, and he plots the cube of that, he gets a straight line. Every single planet falls exactly on this line. There must be something important going on. Now, Kepler could only see, well, Kepler couldn't see anything. Brahe could only see Mercury, Venus, Earth, Mars, Jupiter, Saturn, and Uranus. Okay? None of the other, Pluto and Neptune weren't discovered yet. When we later discovered them, it turns out they fit on the same line. Also, if you look at any asteroid orbiting the sun, it falls on this line also. So what Kepler found was that for all objects orbiting the sun, the cube of the average distance from the sun was directly proportional to the square of the period. He had no idea why. He just found that relationship to be true. Okay? All right. So that was Kepler's 3 laws. In the units we now use, Kepler didn't use these units. In the units we now use, that slope was about 3.4 times 10 to the 18th. And that's meters cubed per second squared. So that's just for fun. All right, now, quick detour. You've heard of Galileo, right? Galileo was not much of a mathematician. He didn't contribute to this heliocentric model of the universe very much, but he did do some interesting things. And one of the things he did was he was sort of an apostle of science, and he really took it to the church and their belief that the church doctrine governed what happened in science. So the church believed that the heavens were perfect because that's where God reigned. And Galileo did some crazy things. He used the newly invented telescope. Galileo actually didn't invent the telescope. It was invented in the Netherlands about 5 years before he did. But apparently he did something novel with his telescope. Instead of staring in the windows of his neighbors, he pointed at the sky, and he discovered there were spots on the sun. Holy macaroni. Why is that a problem? Well, if you think the heavens are perfect, how can there be spots on the sun? He discovered craters on the moon. How is that possible? He discovered 4 moons orbiting Jupiter. They're called the Galilean moons now. How can something be orbiting Jupiter if Earth is the center of the universe? And he also discovered the Milky Way galaxy, which he was pretty sure was a whole bunch of other suns, probably with their own solar systems. So instead of just publishing this nice and quietly to other scientists, he marched down to the local church and started rattling off about how wrong they were about their ways and how the Bible was not a good indicator of science, and got himself in all kinds of trouble. And so we know about Galileo mostly because of the trouble he got in. Copernicus, 50 years before, said that the sun was the center of the universe, not the earth, and he didn't have any trouble. But Galileo got himself in trouble for being a martyr. All right, so all of that happens prior to Newton. Okay, you guys still with me? Yep, you still with me, Noah? All right. Back to Newton. So look at this picture here. Let's have some feedback. We got the moon falling on Newton's head. We got the apple falling on Newton's head. What really bothers Newton in this picture, though, isn't the apple. The apple falling on his head would not have surprised him. It wouldn't have surprised anybody. What bothers Newton in that picture? Any volunteers? Go ahead. Take a shot. What's bothering Newton in that picture?
The moon.
What about the moon?
It's out, but it's also daytime.
That didn't bother him. People have been seeing the moon during the daytime for as long as time existed.
Is it because it's like you can't see all of the moon?
No, I think you probably knew why you couldn't see all the moon. It had to do with geometry of which way the sun was coming from. By the way, the shiny side of the moon always points to the sun. You guys know that? When you see the moon in the sky, whatever side is shiny, the side you can see, the sun is in that direction. So when you see the moon rise, take a look at it, and whichever way think about a normal to the outside edge, whatever way that way is pointing is the direction of the sun. Now, what really bothered Newton was, why does the apple fall, and why does the moon not fall? If the moon is up there, if you had an apple and you put it on a higher tree, you'd still imagine it would fall, right? The moon is just really far out there, but why doesn't it fall? That's what bothered Newton. So Newton was bothered not by a falling apple, but by why the moon itself didn't fall. Okay? So let's look at a little simulation here. This is a thought experiment Newton did to help him understand. Can you guys see the little Earth with the mountain on it? This is the actual picture taken from Newton's notebook. Okay? And on top of the picture has been superimposed a little applet. Suppose you go to the top of this little mountain here and you fire a cannonball. Can you guys see the cannonball there? Did it move? Can you see the little red cannonball here? You can't see it?
It's still a picture of the little mountain, like the actual Google Slides.
Thank you.
Yeah, there we can see it.
Can you see it now?
Yeah.
All right. So I'm going to fire a cannonball. There it goes. Could you see the cannonball go? All right. What happens if you pack more gunpowder in there and you fire it faster? There it goes. Is the cannonball falling? Give me a 1 finger up yes or 2 fingers up no. Is the cannonball falling? Bailey, you're not voting. 1. Yes, the cannonball is falling. What happens if I add more gunpowder and I do this? I fire it. Did it fall? Sure, it fell. What if I put enough gunpowder in it so that it does this? Is the cannonball falling? Sure. Gravity is pulling it down. It's falling. But does it ever hit the earth? No. Duck, Newton. Newton realized that an object moving in a circle around the earth under the influence of gravity was indeed falling. It was falling all the time. But the rate at which it was falling exactly matched the curvature of the earth. So as it fell, the earth curved. And if those two are perfectly worked out, then it can continue to fall forever, always falling but never hitting the earth. Okay? We call that orbital motion. And Newton realized that was the key to understanding why the moon didn't crash into the earth. It was falling in a very special orbit. But the moon is not different than the apple. The moon is pulled on by the earth, just like the apple is. In fact, if he could throw the apple fast enough sideways, it would also go around the earth and not hit the ground. Now, that's not possible for an apple because the atmosphere will slow it down. But if you can get higher than the atmosphere, that's not hard to do at all. We do it all the time now. So a quick comment about weightlessness. What does it mean to be weightless? People think that weightlessness means there's no gravity, and that is not true. Weightlessness means you do not feel a normal force on you. So if you were to climb into an elevator at the top of the Empire State Building and somebody cut all the cables, you and the elevator would accelerate downwards. And for about 5 seconds, you could have a blast. You could, for 5 whole seconds, float around in the elevator. Whee! If you were on a scale, when the cables were cut, the scales would all read 0 because there would be no force pushing up on you because you and the scale and the elevator would all be falling. So we would say you are temporarily weightless. Right before we would say you are permanently dead. But that's beside the point. When we say you are weightless, are we implying that gravity is not pulling on you? No, there's lots of gravity, and you're going to be introduced to it really quickly. But what we mean is there's no normal force pushing back. That's what weightlessness means. So if you ever see, anybody seen a movie where they were floating around in space? What's your favorite space movie? Luke?
Interstellar.
Okay, Interstellar, yeah. So they filmed some of that in a special airplane. I'm glad you didn't say Star Wars. Maybe that's why you were named Luke. I don't know. Is your dad a Star Wars fan? No, all right. Just a coincidence. So there is this airplane. Can you guys see the airplane in the picture here? This is an airplane they use to film movies like Interstellar or Mars or Gravity. So what they do is they fly really high in the sky in the airplane, and then they point the nose towards the Earth, and they just let the airplane fall. It just dives. And for 30 seconds, you are weightless in that airplane. You can film the scenes for 30 seconds. Apollo 13 is my favorite, by the way. If you notice that the film sequences are only about 30 seconds long that are weightless, then they switch to something else, so they have to splice it together. Because after 30 seconds, this airplane's got to turn around and go back up. It takes about 40 minutes to climb all the way back up, and then they dive again. So it has a very special name. Generally, when you keep diving and then pulling out of the dive and going back up, imagine riding a roller coaster over and over. Your stomach starts to feel queasy, right? This airplane is affectionately known as the vomit comet in Hollywood. Basically, for 30 seconds, you video your scene, and then for 40 minutes, the airplane climbs while everybody pukes. Then you get reset, clean up your mess, and start over, okay? So the important thing is to realize that weightlessness does not mean there's no gravity. It means you are falling, okay? So the astronauts on the space station definitely feel gravity. Gravity is pulling on the space station. If there was no gravity pulling on the space station, those astronauts would not circle the Earth. They would be gone. The reason they feel weightless is because they are always falling. Okay? Does that make sense? That's a question the AP likes to harp on, understanding that weightlessness does not imply the absence of gravity. All right, so here's what Newton's got in his toolbox. He understands circular motion. He knows that the force it takes to make an object move in a circle is mv squared over r. And he, like you, knows that this is the mass of the thing that's moving in the circle, right? I'm going to use little m for the mass of the thing moving in a circle. Now, he postulates gravity to look like this. He can't check it in lab because nobody can make measurements that accurate. But he postulates it. He says, I think this is how gravity works. Proportional to the masses, it's diluted by distance, it's a 1 over r squared relationship. The moon gives him a perfect test case to see if his theory of gravity is right. So what he realizes is gravity is the mechanism that can explain the orbits of the planets. Gravity can provide the force that keeps the planets moving in a circle. And if you go with that, you can say that the centripetal force on the moon or on the planets is equal to the force of gravity. Now let's see what that gets us if we work it out. So we're going to do a little calculation here. I'm going to call the object in the middle capital M, and I'm going to call the object that's moving in a circle little m, okay? And for most cases, little m is much smaller than big M, okay? So like for the moon, it's a lot smaller than the Earth. The Earth is a lot smaller than the sun, whatever. Now, the time it takes this thing to go around once, we are going to call the orbital period. That's a special time, so we use capital T for the orbital period. Sorry, every time I go down there to point, it pops up a little menu. So T down there at the bottom is the orbital period. Now, let's start off and see what happens. If we assume that the centripetal force, the force making this green thing move in a circle, is equal to the gravity force, then we can write mv squared over r must equal the gravity force, which is g times big M times little m over r squared. Okay? All right, so help me here. Samuel, break in there. What cancels in that equation?
You can cancel out an r.
Okay.
And you can cancel out the little m.
All right. So it turns out that the little m goes away. Does it matter what the mass of the orbiting object is? No. What if I doubled the mass of the orbiting object? What would happen to the velocity? Not a thing. Okay? The mass doesn't matter. All right. One of the r's canceled also, and so we get this expression here. So if I want to know how fast does this object have to move so that it follows this very special path where it's always falling, but its falling matches the curvature of the planet we're going around. If I want to know what velocity I need, here it is. I just take g, the universal gravitational constant, times the mass of this planet divided by the radius of the orbit, and that tells me the square of the velocity I need. Now, that's not quite what I want right now. For some of the homework problems, it'll ask you what's the velocity, so there you go. The velocity, however, is related to the orbital period. The velocity is the distance you go divided by the time. The distance you go is 1 circumference, which is 2 pi r. And the time it takes to go 1 circumference is the orbital period t. So I'm going to substitute in 2 pi over r divided by t. I'm going to substitute that in for the velocity in this expression right here. So there I go. I get 2 pi r over t. That's the velocity. Square it. I get gm over r. Everybody good so far? Give me a thumbs up if you're still awake. All right. And Madison's still with us. That's good. All right. So if I square everything on the left-hand side, I get this mess. I'm going to cross multiply now to get rid of my fractions. So I get 4 pi squared. I get r cubed because this r over here comes up. I get r cubed, and it equals that. And then, just for fun, I'm going to solve for r cubed. I get gmt squared, divide both sides by 4 pi squared, and here you go. This is what Newton derived as the radius an object must be in, and how that relates to the time it takes to go around, okay? And at that point, he throws up his hands and he says, Eureka! Well, probably not. That was Archimedes, or at least that's how the myth goes. But when Newton gets that result, he knows his understanding of gravity is right. What is it about that result that convinces him that gravity must be right? Any volunteers? What is it about that that's so special? Why would seeing that make him ecstatic? Aubrey, any guesses? No? He's seen that before. Where, Luke?
That one dude's graph.
That one dude's graph. Yeah. Kepler had already shown that for all the planets, the cube of the radius of the orbit was proportional to the square of the period. And not using this at all, just using the theories he thunk up in his head, Newton showed that if gravity was an inverse square law, the radius of the orbit cubed must be proportional to the period squared. And in fact, if you work out what the slope is, it matches pretty close to what the slope was that Kepler found. And so what we have is a theory for, there's absolutely no reason why he should have said, the force of gravity is gm1 m2 over r squared. But if he takes that and he runs with it and he works out what that would imply, he gets perfect agreement with an experiment that Kepler did. So this is how science advances. We think up an idea, we wonder if it's right or not. We apply it. We ask, what would happen if this idea was true? And then we can make predictions. And then experimentalists can test those predictions to see if they actually work. And if they do work, that makes the idea stronger. And the more and more we test an idea, the stronger and stronger it gets. Until eventually, over many years and thousands of tests, it becomes so solid that we believe it is a proper explanation for the way the world works, and we call it a theory, okay? So in science, a theory is an absolutely rock-solid idea that has been tested every which way we can possibly test it. So the theory of gravity. Quantum theory is another theory. So that's how we use the word theory in science. People use it wrong in popular culture. They say, hey, I have a theory about who killed the butler. That's not really the way we use theory. In their case, what we would say is they have a hypothesis about who killed the butler. It's not a theory until it's absolutely certain and proved 14 different ways, at least, or 1 million. Okay, does that make sense? All right, so an idea leads to a prediction. Prediction is confirmed by experimental evidence, which gives us confidence that the idea is valid. We build and extend the idea, which makes more predictions, which be confirmed or discarded. And over these many iterations, our ideas become refined and become a theory. Okay, so that's kind of the idea. All right, let me solve one example problem just to put this all together for you. If I've got a rock, it's out in space. It's a 1 kilogram rock, and it's orbiting a big chunk of ice, and it's 15 meters. What I want to do is find the orbital period. I'm going to do this in parts. Okay, the first thing I'm going to do is I'm going to simply ask, what is the force of gravity between the two objects? So if you know the mass of object 1, the mass of object 2, and the distance between them, you can find the force of gravity. Okay? Give me a thumbs up if you're good so far. Can't see your thumb, Alex. Your computer keeps erasing it. There you go. Keep it right in front of your face. There you go. All right, good deal. So what is the centripetal force causing the rock to move in a circle? So this is a bit of a trick question, guys. If the force of gravity is 5.93 times 10 to the negative 8 newtons, what is the centripetal force? It's the same thing. This is the big idea that Newton used. The centripetal force is the force of gravity. So if you know the force of gravity and somebody says, what's the centripetal force? It's the force of gravity. You don't need to do a new calculation. Now, if you know the centripetal force and you know the mass of the object and you know its radius, you can work out its velocity by solving the centripetal force equation. So this little rock here must be going 9.43 times 10 to the negative 4th meters per second. I just solved this equation, the centripetal force equation, for the velocity. Okay? Give me a thumbs down if you're still good. All right, you're still paying attention. Good deal. All right, now we know the velocity of the object. How far does it travel in one complete orbit? You know what? Grab your calculator. You guys work that out because that's an easy one. The radius is 15 meters. I want to know how far does it travel in one orbit? Go ahead. How far does it travel in one orbit? Radius is 15 meters. Give me a wait 1 minute finger if you don't have it yet. All right, everybody's got it. Okay, Aubrey.
Is it 94.2 meters?
Did anybody else get that? All right, they agree with you. Yep. It's 92.4 meters. So now we can finish our problem. The question was, how long does it take the rock to go all the way around once? We know the distance it's got to go is 94 meters, and we found the velocity was 9.43 times 10 to the negative 4 meters per second. By the way, that's a really small velocity because you can't move very fast because the force of gravity was tiny, right? Remember, the force of gravity was 10 to the negative 8 newtons. If you don't have a lot of force, you can't move very fast. So we know all of these things. We can find the orbital period. The distance it goes equals the velocity times the time. If you know the distance and you know the velocity, you can find the time. It turns out to be about 100,000 seconds or about 28 hours. It would take 28 hours for this rock to circle the planet. Okay? All right, does that all make sense? You're going to solve some problems. And the first problem you're going to solve is you're going to try to figure out how long it takes the Earth to orbit the sun. Okay? Don't cheat and use your prior knowledge. Work it out. The answer is not 24 hours, by the way. It's not how long it takes the Earth to orbit the sun. It's how long it takes the Earth to spin on its own axis. All right, so there's a problem set. Let's stay on this for about 20, 25 minutes or so. Keep solving them. Check your answers as you go. And anything you don't get done by 12:20, we'll call homework, okay? A couple of you are getting a little behind. You haven't done any of the problems this week. You must be just wanting to have a really fun weekend. So this is the end. We're going to review on Monday, take a test on Tuesday, and do our last unit starting Wednesday. So good time to get caught up. All right, I'm going to stop the presentation. Can you guys find the assignment? Anybody, were you able to load it? Alex, can you tell me if there's a link to the example problems in the top? You don't see a link to the exam? Okay.
Not yet, no.
Give me a minute. I will link my examples from lecture so you can see them there, okay? But you guys can do that first one, I think.